Good evening, ladies and gentlemen. How is everyone doing? I'm also well, thank you. So I see a few questions about assignments. So let me look here from Mr. Moore. Good evening, sir. With regards to our assignment on the moon, what can we do if the moon is visible for 4 days and then is no longer visible from our vantage point? So here's a few answering the same question. So unfortunately, that's why you have to plan ahead. That's why I suggested a certain date to start, and that's why I also gave you links to give you the rise and set times of the moon. So unfortunately, then you have to restart again and find a time that is suitable, that a moon will be in your vantage site. Remember, the moon rise and set times will differ by rule of thumb an hour each night, 40 minutes to an hour. So keep that in mind. So unfortunately, you have to restart until you have 10 consecutive days. Then just want to make sure, should our sketches for the assignment be on one page or on separate pages for each day? So on one page. So before we start uh, the lecture this evening, I quickly want to do an experiment. I want to show you guys a video, but I don't know if it's going to work on Blackboard Collaborate. Last year it didn't work, but I received an email saying that I updated Blackboard Collaborate. So there's one or two ways I can try this. The one is I'll share my screen and play it. So please just let me know if it's working, if you can hear anything or not. If that's not working, then I'll try sharing a YouTube tab. If that's not working, then I will give you the links to the videos. So let's try the first video and tell me if it's working or not. Okay, so guys say no sound. That is what I was afraid of. So let me try running it in YouTube and see if that works. So I'm going to change my application screen so I won't be able to see what's happening on the chat. So on the WhatsApp group, if you guys can let me know if it's working or not. No sound still. Input audio source on Blackboard Collaborate. So where do I change the input source for Blackboard Collaborate? So let me see what I can. Okay, so it looks like this is not going to work. For some weird reason, I can't find a setting in my browser to change the input source. So I will try and figure out how this works and show you guys a video. Yes, we can share links, so that's what I will do. After class, I will in any case share these videos, the links to these videos with you. Um, this is actually weird because according to, yes, I've tried right clicking on it. So when I right click on it, the only options I have is mute and always allow on Blackboard Collaborate. Which is totally weird. So currently I'm using Safari, but it's easy for me to swap to a different browser. Stream Party with Google Chrome, that's something I haven't tried before. Okay, Because the documentation I have said if you use Google Chrome, then you can share a tab. Okay, so one thing I can try, I'm just quickly going to log off, and I'm going to log back in with Google Chrome and see if that's going to work. If that's not going to work, then we can continue on with the lecture. So just give me a minute to log into Google Chrome. Okay, I am back in Chrome. Can everybody hear me? Okay, so let's try this again. So apparently now when I say share application screen, it's supposed to work. Now for some weird reason with Chrome I have more options, which is weird and interesting. So let's try this again and see if this is going to work. Okay, so you guys can hear this.
What's the scariest thing you've ever done? Or another way to say it is, what's the most dangerous thing that you've ever done? And
okay, so that's working. Okay, that's weird. So I don't really use Google Chrome. I prefer Safari or Firefox, but looks like this is working. So for tonight's lecture, I'm going to show you a few interesting videos I came across before we continue with the lecture. So this is Colonel Chris Hatfield. Yeah, he holds the record for the person that has the most space shuttle flights under his belt. And this is his story TED Talk of what is the scariest thing that ever happened to him.
Why did you do it? I know what the most dangerous thing is that I've ever done, because NASA does the math. You look back to the first 5 shuttle launches, the odds of a catastrophic event during the first 5 shuttle launches was 1 in 9. And even when I first flew on the shuttle back in 1995, 74 shuttle flight, the odds were still, now that we look back, about 1 in 38 or so, 1 in 35, 1 in 40. Not great odds. So it's a really interesting day when you wake up at the Kennedy Space Center and you're going to go to space that day. Because you realize by the end of the day, you're either going to be floating effortlessly, gloriously in space, or you'll be dead. You go at the Kennedy Space Center, into the suit-up room, the same room that our childhood heroes got dressed in, that Neil Armstrong and Buzz Aldrin got suited in to go ride the Apollo rocket to the moon. And I got my pressure suit built around me and rode down outside in the van heading out to the launch pad, in the Astro van heading out in the launch pad. And as you come around the corner at the Kennedy Space Center, it's normally pre-dawn, and in the distance, lit up by the huge xenon lights, is your spaceship, the vehicle that is going to take you off the planet. And the crew is sitting in the Astro van, sort of hushed, almost holding hands, looking at that as it gets bigger and bigger. We ride the elevator up, and we crawl in on your hands and knees into the spaceship, one at a time, and you sort of worm your way up into your chair and plunk yourself down on your back. And the hatch is closed, and suddenly what has been a lifetime of both dreams and denial is becoming real. Something that I dreamed about, in fact, that I chose to do when I was 9 years old, is now suddenly within not too many minutes of actually happening. And in the astronaut business, the shuttle is a very complicated vehicle. It's the most complicated flying machine ever built. And in the astronaut business, we have a saying, which is, there is no problem so bad that you can't make it worse. And so you're very conscious in the cockpit. You're thinking about all of the things that you might have to do, all the switches and all the wickets you have to go through. And as the time gets closer and closer, this excitement is building. And then about 3.5 minutes before launch, the huge nozzles on the back, like the size of big church bells, swing back and forth. And the mass of them is such that it sways the whole vehicle, like the vehicle's alive underneath you, like an elephant getting up off its knees or something. And then about 30 seconds before launch, the vehicle is completely alive. It is ready to go. The APUs are running. The computers are all self-contained. It's ready to leave the planet. And 15 seconds before launch, this happens. 12, 11, 10, 9, 8, 7, 6, start, 2, 1, boost ignition, and liftoff of the Space Center Discovery, returning to the space station, paving the way for future missions. It is incredibly powerful to be on board one of these things. You are in the grip of something that is vastly more powerful than yourself. It's shaking you so hard you can't focus on the instruments in front of you. It's like you're in the jaws of some enormous dog, and there's a foot in the small of your back pushing you to space, accelerating wildly straight up, shouldering your way through the air, and you're in a very complex place, paying attention, watching the vehicle go through each one of its wickets with a steadily increasing smile on your face. After 2 minutes, those solid rockets explode off, and then you just have the liquid engines, the hydrogen and oxygen, and it's as if you're in a dragster with your foot to the floor and accelerating like you've never accelerated. You get lighter and lighter. The force gets on us heavier and heavier. It feels like someone's pouring cement on you or something, until finally, after about 8 minutes and 40 seconds or so, We are finally at exactly the right altitude, exactly the right speed, the right direction. The engine shut off, and we're weightless. And we're alive. It's an amazing experience. But why would we take that risk? Why would you do something that dangerous? And in my case, the answer is fairly straightforward. I was inspired as a youngster that this is what I wanted to do. I watched the first people walk on the moon, and to me, it was just an obvious thing. I want to somehow turn myself into that. But the real question is, how do you deal with the danger of it and the fear that comes from it? How do you deal with fear versus danger? And having the goal in mind, thinking about where it might lead, directed me to a life of looking at all of the small details to allow this to become possible, to be able to launch and go help build a space station where you are on board a 1 million-pound creation that's going around the world at 5 miles a second, 8 kilometers a second around the world 16 times a day, with experiments on board that are teaching us what the substance of the universe is made of, and running 200 experiments inside, but maybe even more importantly, allowing us to see the world in a way that is impossible through any other means. To be able to look down and have, if your jaw could drop, it would, the jaw-dropping gorgeousness of the turning orb, like a self-propelled art gallery of fantastic, constantly changing beauty that is the world itself. And you see, because of the speed, a sunrise or a sunset every 45 minutes for half a year. And the most magnificent part of all that is to go outside on a spacewalk. You are in a one-person spaceship that is your spacesuit. And you're going through space with the world. It's an entirely different perspective. You're not looking up at the universe. You and the Earth are going through the universe together. And you're holding on with one hand, looking at the world turn beside you. It's like roaring silently with color and texture as it pours by just mesmerizingly next to you. And if you can tear your eyes away from that and you look under your arm down at the rest of everything, it's an unfathomable blackness, with a texture you feel like you could stick your hand into. And you are holding on with one hand, one link to the other 7 billion people. And I was outside of my first spacewalk when my left eye went blind. And I didn't know why. Suddenly my left eye slammed shut in great pain, and I couldn't figure out why my eye wasn't working. I was thinking, what do I do next? I thought, well, maybe that's why we have two eyes. So I kept working. But unfortunately, without gravity, tears don't fall. And so you just get a bigger and bigger ball of whatever that is mixed with your tears on your eye, until eventually the ball becomes so big that the surface tension takes it across the bridge of your nose like a tiny little waterfall and goes goosh into your other eye. And now I was completely blind outside the spaceship. So what's the scariest thing you've ever done? Maybe it's spiders. A lot of people are afraid of spiders. I think you should be afraid of spiders. Spiders are creepy, and they got long, hairy legs. And spiders like this one, the brown recluse, I mean, it's horrible. If a brown recluse bites you, you have one of these horrible big necrotic things on your leg. And there might be one right now sitting on the chair behind you, in fact. And how do you know? And so a spider lands on you, and you go through this great spasmy attack because spiders are scary. But then you could say, well, is there a brown recluse sitting on the chair beside me or not? I don't know. Are there brown recluses here? So if you actually do the research, you find out that in the world, there are about 50,000 different types of spiders. And there are about 24 that are venomous out of 50,000. And if you're in Canada, because of the cold winters, here in BC, there's about 720, 730 different types of spiders. And there's one that is venomous. And its venom isn't even fatal. It's just kind of like a nasty sting. And that spider, not only that, but that spider has beautiful markings on it. It's like, I'm dangerous. I got a big radiation symbol on my back. It's the black widow. So if you're even slightly careful, you can avoid running into the one spider, and it lives close to the ground. When you're walking along, you are never going to go through a spider web where a black widow bites you. Spider webs like this, it doesn't build those. It builds them down in the corners. And this one black widow, because it's the female spider eats the male. It doesn't care about you. So in fact, the next time you walk into a spider web, you don't need to panic and go with your caveman reaction. The danger is entirely different than the fear. And how do you get around it, though? How do you change your behavior? Well, next time you see a spider web, have a good look, make sure it's not a black widow spider, and then walk into it. And then you see another spider web and walk into that one. It's just a little bit of fluffy stuff. It's not a big deal. And the spider that may come out is no more threat to you than a ladybug or a butterfly. And then I guarantee you, if you walk through 100 spider webs, you will have changed your fundamental human behavior, your caveman reaction. And you will now be able to walk in the park in the morning and not worry about that spider web or into your grandma's attic or whatever, into your own basement. And you can apply this to anything. If you're outside on a spacewalk and you're blinded, your natural reaction would be to panic, I think. It would make you nervous and worry. But we had considered all the venom, and we had practiced with a whole variety of different spider webs. We knew everything there is to know about the spacesuit, and we trained underwater thousands of times. And we don't just practice things going right, we practice things going wrong all the time, so that you are constantly walking through those spider webs, and not just underwater, but also in virtual reality labs with the helmet and the gloves, so you feel like it's realistic. So when you finally actually get outside on a spacewalk, it feels much different than it would if you just went out first time. And even if you're blinded, your natural panicky reaction doesn't happen. Instead, you kind of look around and go, okay, I can't see, but I can hear, I can talk. Scott Perezinski's out here with me. He could come over and help me. We actually practiced incapacitated crew rescue. So he could float me like a blimp and stuff me into the airlock if we had to. I could find my own way back. It's not nearly as big a deal. And actually, if you keep on crying for a while, whatever that guck was that's in your eyes starts to dilute, you can start to see again. And Houston, if you negotiate with them, they will let you then keep working. And we finished everything on the spacewalk. And when we came back inside, Jeff got some cotton batting and took the crusty stuff around my eyes. And it turned out it was just the anti-fog, sort of a mixture of oil and soap that got in my eye. And now we use Johnson's No More Tears, which we probably should have been using right from the very beginning. But the key to that is by looking at the difference between perceived danger and actual danger. Where's the real risk? What is the real thing that you should be afraid of? Not just a generic fear of bad things happening. You can fundamentally change your reaction to things so that it allows you to go places and see things and do things that otherwise would be completely denied to you. Where you can see the hard pan south of the Sahara, or you can see New York City in a way that is almost dreamlike, or the unconscious gingham of Eastern Europe fields, or the Great Lakes as a collection of small puddles. You can see the fault lines of San Francisco and the way the water pours out under the bridge, just entirely different than any other way that you could have if you had not found a way to conquer your fear. You see a beauty that otherwise never would have happened. It's time to come home. At the end, this is our spaceship, the Soyuz, that little one. 3 of us climb in, and then this spaceship detaches from the station and falls into the atmosphere. These 2 parts here actually melt. We jettison them and they burn up in the atmosphere. The only part that survives is the little bullet that we're riding in, and it falls into the atmosphere. And in essence, you are riding a meteorite home. And riding meteorites is scary, and it ought to be. But instead of riding into the atmosphere, just screaming like you would if suddenly you found yourself riding a meteorite back to Earth, instead, 20 years previously, we had started studying Russian. And then once you learned Russian, then we learned orbital mechanics in Russian. And then we learned vehicle control theory. And then we got into the simulator and practiced over and over and over again. And in fact, you can fly this meteorite and steer it and land in about a 15-kilometer circle anywhere on the Earth. So in fact, when our crew was coming back into the atmosphere inside the Soyuz, we weren't screaming, we were laughing. It was fun. And when the great big parachute opened, we knew that if it didn't open, there's a second parachute, and it runs on a nice little clockwork mechanism. So we came back, we came thundering back to Earth, and this is what it looked like to land in a Soyuz in Kazakhstan.
And you can see one of those search and recovery helicopters. Once again, that helicopter, part of a dozen such Russian Mi-8 helicopters. Touchdown, 3:14 and 48 seconds a.m. Central Time.
And you roll to a stop as if someone threw your spaceship at the ground and it tumbles end over end. But you're ready for it. You're in a custom-built seat. You know how the shock absorber works. And then eventually the Russians reach in, drag you out, plunk you into a chair, and you can now look back at what was an incredible experience. You have taken the dreams of that 9-year-old boy, which were impossible and dauntingly scary, dauntingly terrifying, and put them into practice and figured out a way to reprogram yourself, to change your primal fear so that it allowed you to come back with a set of experiences and a level of inspiration for other people that never could have been possible otherwise. Just to finish, they asked me to play that guitar. I know this song, and it's really a tribute to the genius of David Bowie himself, but it's also, I think, a reflection of the fact that we are not machines exploring the universe. We are people, and we're taking that ability to adapt and that ability to understand and the ability to take our own self-perception into a new place. This is Major Tom to ground control. I've left forevermore, and I'm floating in a most peculiar way. And the stars look very different today. For here am I floating a last glimpse of the world. Planet Earth is blue, and there's so much left to do. Fear not.
So what did you guys think? So that is just one experience from Colonel Chris Hadfield. So far as I understand, Colonel Chris Hadfield, I think he had 12 or 13 space shuttle missions under his belt. And Soyuz missions. So now that I know how this is working, every lecture I can show you a video. That's true. Mr. Van den Berg, I think you made a comment earlier. Yes, I've received your email. I will reply to it tonight as well. So for tonight, I'm just going to make sure there's a video, one more video I would like to play. I'm just going to make sure I find it.
It's Professor Dave.
Okay, I have one more video I would like to show you guys tonight.
Twinkle, twinkle, little star. Oh, I know who you are. At first glance, stars pretty much all look alike. Twinkly dots scattered across the sky. But as I talked about in episode 2, when you look more closely, you see differences. The most obvious is that some look bright and some faint. As I said then, sometimes that's due to them being at different distances, but it's also true that stars emit different amounts of light too. If you look through binoculars or take pictures of them, you'll see that they're all different colors too. Some appear white, some red, orange, blue, and for a long time, the reason for this was a mystery. In the waning years of the 19th century, astrophotography was becoming an important scientific tool. Being able to hook a camera up to a telescope and take long exposures meant being able to see fainter objects, revealing previously hidden details. It also meant that spectroscopy became a force, say it with me now, for science! A spectrum is the result when you divide the incoming light from an object into individual colors or wavelengths. This reveals a vast amount of physical data about the object. But in the late 1800s, we were only just starting to figure that out. Interpreting stellar spectra was a tough problem. The spectrum we measure from a star is a combination of two different kinds of spectra. Stars are hot, dense balls of gas, so they give off a continuous spectrum. That is, they emit light at all wavelengths. However, stars also have atmospheres, thinner layers of gas above the denser inner layers. These gases absorb light at specific wavelengths from the light below, depending on the elements in them. The result is that the continuous spectrum of a star has gaps in it, darker bands where different elements absorb different colors. At first, stars were classified by the strengths of their hydrogen lines. The strongest were called A stars, the next strongest B, then C, and so on. But in 1901, a new system was introduced by spectroscopist Annie Jump Cannon, who dropped or merged a few of the old classifications and then rearranged them into one that classified stars by the strengths and appearances of many different absorption lines in their spectra. A few years later, physicist Max Planck solved a thorny problem in physics, showing how objects like stars give off light of different colors based on their temperature. Hotter stars put out more light at the blue end of the spectrum, while cooler ones peaked in the red. Around the same time, Bengali physicist Meghnad Saha solved another tough problem: how atoms give off light at different temperatures. 2 decades later, the brilliant astronomer Cecilia Payne-Gaposchkin put all these pieces together. She showed that the spectra of stars depended on the temperatures and elements in their atmospheres. This unlocked the secrets of the stars, allowing astronomers to understand not just their composition, but also many other physical traits. For example, at the time, it was thought that stars had roughly the same composition as the Earth. But Payne-Gaposchkin showed that stars were overwhelmingly composed of hydrogen, with helium as the second most abundant element. The classification scheme proposed by Cannon and decoded by Payne-Gaposchkin is still used today, and arranges stars by their temperature, assigning each a letter. Because they were rearranged from an older system, the letters aren't alphabetical. So the hottest are O-type stars, slightly cooler are B, followed by A, F, G, K, and M. It's a little weird, but many people use the mnemonic, "Oh, be a fine guy, kiss me," or "Oh, be a fine girl, kiss me," to remember it, which was dreamed up by Annie Jump Cannon herself. Each letter grouping is divided into 10 subgroups, again according to temperature. We've also discovered even cooler stars in the past few decades, and these are assigned the letters L, T, and Y. The Sun has a surface temperature of about 5,500 degrees Celsius and is a G2 star. A slightly hotter star would be a G1, and a slightly cooler star a G3. Sirius, the brightest star in the night sky, is much hotter than the Sun and is classified as an A0. Betelgeuse, which is red and cool, is an M2. Stars come in almost every color of the rainbow. Hot stars are blue, cool stars red. In between, there are orange and even some yellow stars. But there are no green stars. Look as much as you want, and you won't find any. It's because of the way our eyes see color. A star can put out lots of green light, but if it does, it'll also emit red, blue, and orange. And our eyes mix those together. Because if you look at the Sun's spectrum, it actually peaks in the green. Isn't that weird? The Sun puts out more green light than any other color, but our eyes see all the mixed colors together as white. Wait, what? White? You may be thinking the Sun is actually yellow. Not really. The light from the Sun is white, but some of the shorter wavelengths like purple and blue and some green get scattered away by molecules of nitrogen in our air. Those appear to be coming from every direction but the Sun, which is why the sky looks blue. The sun doesn't emit much purple, so the sky doesn't look purple, and the green doesn't scatter as well as blue. That gives the sun a yellowish tint to our eyes. And looking at the sun is painful anyway, so it's hard to accurately gauge what color it appears. That's also why sunsets look orange or red. You're looking through more air on the horizon to see the sun, so all the bluer light is scattered away. So we can use spectra to determine a lot about a star. But if you combine that with knowing a star's distance, things get amazing. You can measure how bright the star appears to be in your telescope, and by using the distance, you can calculate how much energy it's actually giving off, what astronomers call its luminosity. An intrinsically faint light looks bright if it's nearby, but so does a very luminous light far away. By knowing the distance, you can correct for that and figure out how luminous the objects actually are. This was, no exaggeration, the key to understanding stars. A lot of a star's physical characteristics are related. Its luminosity depends on its size and temperature. If two stars are the same size, but one is hotter, the hotter one will be more luminous. If two stars are the same temperature, but one is bigger, the bigger one will be more luminous. Knowing the temperature and distance means knowing the stars themselves. Still, it's a lot of data. A century ago, spectra were taken of hundreds of thousands of stars. How do you even start looking at all that? The best way to understand a large group of objects is to look for trends. Is there a relationship between color and distance? How about temperature and size? You compare and contrast them in as many ways possible and see what pops up. I'll spare you the work. A century ago, astronomers Einar Hertzsprung and Henry Norris Russell made a graph in which they plotted a star's luminosity versus its temperature. When they did, they got a surprise, a very strong trend. This is called an HR diagram, after Hertzsprung and Russell. It's not an exaggeration to call it the single most important graph in all of astronomy. In this graph, really bright stars are near the top, fainter ones near the bottom. Hot blue stars are on the left, and cool red stars on the right. The groups are pretty obvious. There's that thick line running diagonally down the middle, the clump to the upper right, and the smaller clump to the lower left. This took a long time to fully understand, but now we know this diagram is showing us how stars live their lives. Most stars fall into that thick line, and that's why astronomers call it the main sequence. The term is a little misleading. It's not really a sequence per se, but as usual in astronomy, it's an old term and we got stuck with it. The reason the main sequence is a broad, long line has to do with how stars make energy. Like the sun, stars generate energy by fusing hydrogen into helium in their cores. A star that fuses hydrogen faster will be hotter because it's making more energy. The rate of fusion depends on the pressure in a star's core. More massive stars can squeeze their cores harder, so they fuse faster and get hotter than low-mass stars. It's pretty much that simple, and that explains the main sequence. Stars spend most of their lives fusing hydrogen into helium, which is why the main sequence has most of the stars on it. Those are the ones merrily going about their starry business of making energy. Massive stars are hotter and more luminous, so they fall on the upper left of the main sequence. Stars with lower mass are cooler and redder, so they fall a little lower to the right, and so on. The sun is there too, more or less in the middle. What about the other groups? Well, the stars on the lower left are hot, blue-white, but very faint. That means they must be small, and we call them white dwarfs. They're the result of a star like the sun eventually running out of hydrogen fuel. We'll get back to them in a future episode. The stars on the upper right are luminous but cool. They must therefore be huge. These are red giants, also part of the dying process of stars like the sun. Above them are red supergiants, massive stars beginning their death stage. You can see some stars that are also that luminous, but at the upper left. Those are blue supergiants. They're more rare, but they too are the end stage for some stars. And again, we'll get to them soon enough in a future episode. But I'll just say here that it doesn't end well for them. But on a brighter note, we literally owe our existence to them. And this implies something very nifty about the HR diagram. Stars can change position on it. Not only that, but massive stars versus low-mass stars age differently and go to different parts of the HR diagram as they die. In many ways, the diagram allows us to tell at a glance just what a star is doing with itself. This difference between the way low-mass stars like the sun and higher-mass stars age is actually critical to understanding a lot more about what we see in the sky. So much so that they'll be handled separately in later episodes. I'm sorry to tease so much about what's to come, but this aspect of stars, finally understanding them physically, was a major step in astronomy, leading to understanding so much more. And don't you worry, we'll get to all that. Today you learned that stars can be categorized using their spectra. Together with their distance, this provides a wealth of information about
So this is a video of what we are currently busy with. So question, what is the third thing luminosity depends on? So luminosity depends on temperature and size, but the temperature and size also is dependent on pressure. Pleasure. So let's continue where we left off last week. So let me just find a place in these slides. So this guy's YouTube channel, if you just search on YouTube Astronomy Basics, then this guy will pop up. Yes, crash course. So last week we ended off with this reasoning by numbers. So this evening we're going to talk about giants, supergiants, and red dwarfs that we also heard about a little bit in this video we just watched. The question in reasoning with numbers 8.3 previously that relates luminosity, temperature, and radius of the star can be used to draw precise lines of constant radius across the HR diagram. And these lines slopes down and to the right across the diagram because cooler stars are fainter than hotter stars of the same size. So here is our normal HR diagram that you will see many times from this point forward. Our main sequence, our giants, the supergiants, and our white dwarfs. But here we can see stars, our supergiants, has a 10 solar radius, so 10 times the radius of the sun, 100 times radius of the sun, 1,000 times radius of the sun, and over here 0.001 radius of the sun. The previous figure plots the luminosities and temperatures of a number of well-known stars along with lines of constant radius. For example, locate a line labeled 1R, so 1 solar radius, and notice that it passes through the point representing the sun. Any star whose point is located along this line has a size equal to the sun. Next, look at the rest of the stars along the main sequence. They range from 10th the size of the sun to about 10 times as large. Even though the main sequence slopes dramatically down to the right across the diagram, most main sequence stars are similar in size. In contrast, the white dwarfs at the lower left of the diagram are extremely small, only 1/100th of the diameter of the sun, about the size of Earth, and the giants and supergiants at the upper right are extremely large compared to the stars of the main sequence. Notice the great range of sizes among stars. The largest stars are 100,000 times larger than the tiny white dwarfs. If the sun were a tennis ball, the white dwarfs would be grains of sand and the largest supergiants would be as big as football fields. So luminosity and luminosity spectral classification. Spectra of stars contains clues not only about their temperature and composition. You can also use a star spectrum to determine whether it is a main sequence star, a giant, or a supergiant. The larger a star is, the less dense its atmosphere is, and that affects the widths of spectral lines. Atoms collide often in a dense gas, their energy levels become distorted, and their spectral lines are broadened. Hydrogen-Bowman lines are an example. So how do these supergiants not collapse in on themselves? That's exactly what happens at the end of their life cycle. So in the following lectures, we will discuss how these supergiants maintains its form and presence until the end of its life, how it collapses and forms a black hole. So in this image, we'll see the spectra of a supergiant, a giant, and a main sequence star. In a spectrum of a main sequence star, the Balmer lines are broad because the star's atmosphere is dense and hydrogen atoms collide often. In the spectrum of a giant star, the lines are narrow because the giant star's atmosphere is less dense and the hydrogen atoms collide less often. In the spectrum of a supergiant star, the Balmer lines are very narrow. You can look at a star's spectrum and tell roughly how big it is. The size categories derived from spectra are called luminosity classes, because the size of the star is the dominating factor in determining luminosity. Supergiants, for example, are very luminous because they are very large. The luminosity classes are represented by Roman numerals. So I for supergiants, through V that means 5 for main sequence stars. With supergiants further divided into types 1A, 1B as follows. So here's the luminosity. So 1A, supergiant. 1B, luminous supergiant, supergiant. Type 2, luminous giant. Type 3, giant. Type 4, subgiant. Type 5, main sequence. Astronomers can measure the stellar parallax of nearby stars, but most stars are too distant to have measurable parallaxes. These distances can be estimated from the star's spectral type, luminosity class, and apparent magnitude in a process called spectroscopic parallax. Spectroscopic parallax is potentially a confusing term because it does not involve an actual measurement of parallax shifts, but it's a method to tell you the distance to the star. Spectroscopic parallax relies on the location of the star in the HR diagram. If you record a spectrum of a star, you can determine its spectral class, and that tells you its horizontal location in the HR diagram. You can also determine its luminosity class by looking at the widths of its spectral lines, and that allows you to estimate the star's vertical location in the diagram. Once you plot the point that represents the star in the HR diagram, you can read off its absolute magnitude. For example, famous star Betelgeuse has an apparent magnitude of about 0.4. It's classified as an M2-1b. You can find Betelgeuse plotted in a previous figure at an absolute magnitude of about -6. The difference between Betelgeuse apparent and absolute magnitudes is therefore 0.4 minus 6 or 6.4. So its distance calculated from magnitude distance formulas, the reasoning of numbers we did, is about 190 parsecs. A combination of parallax measurements made by Hipparcos satellite and radio telescopes yields a distance of 197 parsecs, with uncertainty of 24%. So the result derived from the spectroscopic parallax method is not too bad. Obviously, a real measurement of the parallax is better, but for distant stars, spectroscopic parallax is often the only way to find their distances. To further understand stars, you need to find out how much matter they contain. That is, their masses. Gravity is the key to determining star masses. Matter produces a gravitational field, and you can figure out how much matter a star contains if you watch another object move through that star's gravitational field. To find the masses of stars, you need to study binary stars, so pairs of stars that orbit each other. Have you guys heard of binary stars before? Okay, so in this sharing a PDF currently with animation, and so I'm just going to open up the presentation in Keynote and share it to see if this will work a little bit better, showing the animation. Okay, so I'm going to just quickly share my application screen. So you guys should be able to see this. So this is what we call a binary star. So we will have two stars orbiting one another. Are you guys still following? Awesome. So contrary to belief, most stars in the night sky are actually binary stars. And the closest star to us, Alpha Centauri, that's also a binary star. One of the most lowest star in the Southern Cross is also a binary star. So if you make it out, it looks like only one star, but if you look through a telescope or a pair of binoculars, you'll see 2 points close to each other, and it's actually two stars orbiting one another. Yes, they really orbit each other. So you have two masses, and they orbit their central mass at a point between them where everything is in equilibrium. So let me get back to our normal slides. Share files. This is unfortunately the only drawback of Blackboard Collaborate. You can't jump between files. Okay, so if our solar system was a binary system, would it be possible for it to be daylight throughout the whole Earth? Unfortunately not. It's actually quite rare for binary star systems to have planets around them because of the gravitational effect of the two stars. But if we were, say, we had a binary star system, then Earth would be in orbit around both stars. So with sunset, sunrise, we will have two stars close to one another, but you still have day, night, daytime, nighttime. If you want to have daytime all the time, then the planet would have been in orbit around one or our orbit around other two, and that would be chaotic and not possible. So it will be an orbit around both stars. So, is it possible for two stars to merge or collide? Yes, that happens as well. And we're going to discuss that in the following chapters as well. So what would happen if one of them goes supernova? So that's what's interesting for these stars to go supernova is Interesting stuff happens to these binary systems if they are close enough. So one star could steal energy from another star, and you can have energy transfer, and that will keep the system stable. But for them to become supernova, one star must eat basically the other star, and then it can go supernova. But we'll discuss all of that in following chapters as well. I really like your guys' questions. Bit off topic. I'm sure you've all seen about Michael Collins last week. So I assume everybody is familiar with Michael Collins. So Michael Collins is one of the astronauts that went with Neil Armstrong and Buzz Aldrin to the moon. So while Buzz Aldrin and Neil Armstrong was the first persons on the moon, he was in the command module, still orbiting the moon, waiting for Neil and Buzz to return to the module. And he passed away last week at the age of 90 years old. So here we can see binary star, the general binary star. So to measure the mass of a binary star, you first need to understand its orbital motion. So here we will have, in this image, we will have star B, we will have star A, and they will both orbit their common center of mass. So looking at this, one thing to notice is the largest star will be closer to the center of mass. You can think about it's the same principle as the moon that orbits Earth. Both of them have a center of mass, but that's located below Earth's surface. But in this point, it won't be located below one of those surfaces, but a distance between them. To find the total mass of a binary star system, you need to know the sizes of the orbit and the orbital period. The length of time the stars take to complete one orbit. The larger the orbits are, the shorter the orbital period is. The stronger the star's gravity must be to hold each other in orbit. For example, if two stars whirl rapidly around each other in small orbits, then their gravity must be very strong to prevent their flying away from each other. Such stars would have to be very massive. From the size of the orbits and the orbital period, you can figure out the masses of the stars as explained in the previous reasoning with numbers. So here is another reasoning with numbers to keep in mind for tests and exams. So to calculate the masses of binary stars, Johannes Kepler's third law of So please explain how larger orbit equals shorter orbital period. Okay, so let me get the whiteboard out. So what that means is if we have two stars, so here is one star, here is a smaller star, here is the central point they both are orbiting. So what that means is one star is orbiting another star. So it means is the closer we are to this point, the faster the orbit is. So let me just draw. So this would orbit the central point like this. This would orbit the central point like this. So this will keep the stars closer. So one way to, another way, just let me simplify this a little bit. Let me simplify this. So if I simplify this as as this, and the orbital central point is below the surface, for example, the star will move rapidly around the other star because it's so close. It means the gravitational pull of the stars are large, meaning that the orbital period will be much faster because they are closer to one another. But if you have the same system and you have the one and the other one far away, meaning the gravitational pull between the two is a lot less, means it will move around slow in orbit, meaning the stars' sizes are physically smaller because the gravitational pull is not that large, and these two stars are further away from each other. Does that help a little bit? Awesome. So let me find the slide again. I don't know why every time I open up a different application, Blackboard loses the spot in the slides. So let's calculate. So Johannes Kepler's third law of orbital motion worked only for the planets in our solar system. When Isaac Newton realized that mass produces gravitational attraction that causes orbits, he made that law into a general principle. Newton's version of Kepler's third law applies to any pair of objects that orbit each other. The total mass of two objects is related to the average distance, a, between them, and the orbital period of p. If the masses are ma and mb, then ma plus mb equals the distance divided to the power of third power to the period to the second power. In this formula, a is expressed in AU and p is expressed in years and m in solar masses. Notice how this formula is related to Kepler's third law. You guys can look back when you are studying. Almost all of the masses in the solar system is in the sun. If you apply this formula to any planet in our solar system, the total mass is one solar mass. Then the formula becomes p squared equals a to the third, which is Kepler's third law. This formula lets you find the masses of binary stars. You must know the distance to the binary system to be able to convert the average angular separation between the two stars in AU. Using that and the orbital period in units of years, the sum of the masses of the two stars in solar units is just a to the power 3 over p to the power 2. So example, if you observe a binary system with a period of 32 years and average separation of 16 AU, what is the total mass? The solution is you just plug it into the formula and that equals 4 solar masses. Example B. Let's call the two stars in the previous example A and B. Suppose star A is 12 AU away from the center of mass and star B is 4 AU. What are the individual masses? The solution. The ratio of the masses must be 12 to 4, which equals the ratio of 3 to 1. What two numbers add up to 4 and have the ratio of 3 to 1? Star B must be 3 solar masses and star A must be 1 solar mass. Do you guys understand this or still following? Awesome. Each star in a binary system moves in its own orbit around the system's center of mass. The balance point of the system. If one star is more massive than its companion, the more massive star is closer to the center of mass and travels in a smaller orbit, while the lower mass star whips around a larger orbit. The ratio of masses of the stars Ma and Mb is equal to Rb over Ra, the inverse ratio of the radii of the orbits. If one of the stars has an orbit twice as large as the other star's orbit, then it must be half as massive. The period and the total size of the two stars' orbits tells you the sum of the masses, and the relative sizes of the two orbits give you the ratio of their masses. That is enough that is enough to let you determine individual masses of each star. So what makes the formula become okay, so let me go back. So the formula becomes, so this is Kepler's law. So what happens is we want to find the masses. So we are looking here for so what happens in this example is, let me get something to write out. So we are looking at one solar mass. So that means one solar mass, Ma plus Mb equals 1. And you just multiply this over. So then you get p to the power of 3 equals A to the power of 3. So example 2 seems a bit complex. So let's go to example B. Let's call the two stars in the previous example A and B. So the previous examples, if you observe a binary system with a period of 32 years and an average separation of 16 AU, what is the total mass? So we calculated the total mass as 4 solar masses. So now let's call the two stars in the previous example star A and star B. Suppose that A is 12 AU from the center of mass and B is 4 AU away. What are the individual masses? So we calculated the total mass of the system is 4 solar masses. So now we know the one is 16 AU away and the other one, so let me just so average separation of 16 AU, what is the total mass? The total mass is there's just a period, but now we know the one is, suppose the star A is 12 AU away from the center of mass and star B is 4 AU away. That means we have a ratio of 12 to 4, right? So now we can simplify this as a ratio of 3 to 1. But we know the maximum mass of the system is 4 solar masses, right? So now we know what ratio we need to be to get 4 solar masses. So now we know the bigger star needs to be 3 solar masses and the smaller star needs to be 1 solar mass. And if you add them together, we get 4 solar masses. So we can say this is star A and this is star B. Does that help? Does that answer your question? Awesome. Okay, so everybody following, everybody comfortable with where we are right now? Okay. Figuring out the masses of stars in a binary system has some further complications. The orbits of the two stars may be elliptical, and although the orbits lie in the same plane, the plane can be tipped at an unknown angle to your line of sight, further distorting the observed shapes of the orbits. Astronomers must find ways to correct for those distortions. In addition, astronomers analyzing binary systems must first find the distances to find them, so they can estimate the true size of orbits in astronomical units. Finding the masses of binary stars requires a number of steps to get from what you can observe to what you really want to know, the masses. Although there are many different kinds of binary stars, 3 types are especially useful for determining stellar masses. These are discussed separately in the next sections. So the first one is visual binary systems. In a visual binary systems, 2 stars are separately visible in the telescope. Only a pair of stars with large orbits can be separated visually. If the orbits are small, the telescope cannot resolve the star image, and you see only a single point of light. In a visual binary system, you can see each star moving around its own orbit around a center of mass. Astronomers study visual binary systems by measuring the positions of the 2 stars over the course of many years to map the orbits. So here we can see a visual binary system. So here we can see Sirius A, the bright star, and Sirius B, the less white star, the white dwarf. And this is what happens when you look at the star Sirius, that is also a binary system. So over the years, astronomers can watch 2 stars move and map their orbits. So you can see a line between the stars always passes through the center of mass of the system. The star closest to the center of mass is the more massive one. The elliptical orbits are tipped at an angle to our line of sight. So here we can see a tip to us. So here's this one star and the other star and a common central mass. Visual binary systems are common. More than half of the stars are members of binary star systems, and many of those are visual binaries. However, many of those systems cannot be analyzed completely. For example, famous star Polaris have 2 stellar companions. One of the stars that orbits Polaris has an orbital period estimated to be over 1,000 years, so the exact size and period are not well known. The other companion is so close to Polaris that is hardly distinguishable even with the Hubble Space Telescope. Everyone still following? Okay. So next we get spectroscopic binary systems. If the stars in a binary system are very close together, telescopes limited by diffraction and seeing may reveal only a single point of light. By looking at a spectrum which is formed by light from both stars and contains spectral lines from both, astronomers can sometimes tell that there are 2 stars present and not one. Such pair of stars is spectroscopic binary. So keep in mind that half of the stars in the night sky are binary stars or binary systems. So can 2 stars be binary stars no matter how huge a difference in the sizes is? Yes. So it all depends if there are stable orbits around each other. So meaning a central mass. But sometimes these binary systems is not stable, and we will discuss that as well. Most known binary systems are spectroscopic binaries. Many of the familiar stars in the sky, apparently single stars, are actually 2 or more stars orbiting each other. So looking at these stars right here, this looks like 2 stars close to one another. But looking at the telescopic view, we will see these are binary stars. But looking closer, we can see there's something hidden. So at the bend of the handle of the Big Dipper lies a pair of stars, Mizar and Alcor. Through a telescope, you can discover that Mizar is a fainter companion and is so a member of the visual binary system. Adaptive optics observation reveal a faint close companion of alcohol, not pictured in this diagram. Spectra of MISA sometimes show single spectral lines, so in the top strip, and sometimes show double lines in the bottom strip, indicating that the main star of the visual binary system is itself a spectroscopic binary system rather than a single star. And also in these spectroscopic binaries, we can use red and blue shifting to determine how they are orbiting one another. So yes, we can see stars orbiting each other produce spectral lines with Doppler shifts. As the stars move in their orbits, the Doppler shifts of the spectral lines. So here we can see star B is moved, so if our point of view is from here, we can see star B is moving away from us, so it's red shifted, and star A moving towards us is blue shifted. So here we can see star B is still moving away from us, so red shifted. Star A is moving towards us, so it's blue shifted. Here we can now see star B is moving away from us, so it's blue shifted, and star A is moving towards us, so it's red shifted. Here star B is moving away from us, blue shifted, and star A is moving away from us, so it's red shifted. So everybody's still following. Okay. And now the last one, and my favorite, is the eclipsing binary system. As mentioned earlier, the orbits of the two stars in the binary system always lie in a single plane. If that plane is nearly edged onto Earth, then the stars will appear to cross in front of each other. Imagine a model of a binary star system in which a cardboard disk represents the orbital plane and balls represent the stars. If you see the model from the edge, then the balls that represent the stars can move in front of each other as they follow their orbits. Seen from Earth, the two stars are never visible separately, only as a single point of light. But as the stars repeatedly block each other's light from our point of view, total brightness of the point of light periodically decreases. Such a pair of stars is called an eclipsing binary. So this is what's meant. So the one will move in front of the other one. So I'm just going to share my application screen. I have a nice animation I can show you guys from this. So this is how it will look like with eclipsing binary stars. You have a larger star and a smaller star. So as you can see, when the big one is in front, you'll see a big dip, small dip, big dip, small dip in the brightness of the stars. The second dip is because the one is blocking the other one. So here, the big one blocks the small one, and here the small one blocks the big one. So that is the total brightness of the system. So it will be the brightest when these two stars are next to each other. So yes, the smaller one is being blocked by the larger one, and here the larger one is being blocked by the small one. So let me get back to the slides. So I have to find my place again. So the stars are both emitting light. How do they block one's light? So if this star moves in front of that one, we won't be able to see that one. It's one object blocking another object, if that makes sense. So you can think about it if you have a soccer ball in one hand and if you have a soccer ball in one hand, so let me just put on my camera so I can explain with my hands. So you guys should be able to see me now. So what happens is if you have a soccer ball in one hand and then a golf ball in the other hand, so what happens is if you rotate it this way, you'll see the small one in front of the big one, so you'll have, it's almost like a eclipse on the big one. But if you do the other way around, you won't be able to see the small one behind the big one, and that's why you are blocking the other one. I hope that helps a little bit. So the resulting variation in the brightness of the system, it's a pleasure. So the resulting variation in the brightness of the system is shown as a graph of brightness versus time, so you get a light curve. The light curves of eclipsing binary systems can be different to analyze, but they contain tremendous amount of information. The eclipsing binary angle consists of hot B star and a cooler K star. The eclipses are partial, meaning that neither star is completely hidden during eclipses. The orbit here is drawn as if the cooler star were stationary. The relative size of the Sun is indicated in a small open circle. So here we can see the one star, no eclipse. So here we can see the dip of the one and the dip again. So here we can see the cooler star is partially hidden. That is what I just basically explained, with one star being blocked by another star. The observed light curve of the binary star Sherpa shows that the two stars are so close together that gravity distorts their shapes. Slightly variations in the light curve reveal the presence of transient dark spots at specific places on the light star's surface. The upper curve shows what a light curve would look like if there were no spots. So now putting everything together and getting a census of the stars. So everything we learned tonight, how do we wrap, and tonight and in last week's lecture, how do we wrap up everything? So you have learned how to find the luminosities, temperatures, sizes, and masses of stars. Now you can put all those data together to point a family portrait of the stars. As in any family portrait, both similarities and differences are important clues to the history of the family. As you begin trying to understand how stars are born and how they die, ask a simple question. What is the average star like? Answering that question is both challenging and illuminating. So, I want to ask you guys, how would you classify an average star? So how would you classify an average star, and how would you determine it's an average type star? Yes, the Sun is an example of an average type star. You are completely correct. But what makes an average type star an average type star, and how do you determine that? Okay, so if you want to know what an average person thinks about a certain subject, you take a survey. If you want to know what an average star is like, you need to survey the stars. Such surveys reveal important relationships among the family of stars. Not many decades ago, surveying a large number of stars was exhausting task, but modern computers have changed that. Specially designed telescopes controlled by computers can make millions of observations per night, and high-speed computers can compile these data into easy-to-use databases. Those surveys produce mountains of data that astronomers can mine, while searching for relationships within the family of stars. What could you learn about stars from a survey of stars near the Sun? Astronomers have evidence that the Sun is a typical place in the universe. Therefore, such a survey could reveal general characteristics of stars everywhere and might reveal the unexpected process of governing the formation and evolution of stars. Surveying of stars. There are three important things to notice. Number one, making a good survey is difficult because you must be sure you get a good sample. If you don't survey enough stars, or if you miss some kinds of stars, your survey might produce biased results. Secondly, luminous stars are rare. The most common types of stars are the low luminosity red dwarfs. Then thirdly, a careful survey reveals that what you see in the sky is deceptive. Most of the bright stars in the sky are not typical stars, but indeed are highly luminous giant and supergiant stars that can be seen from great distances. If you survey enough stars and plot the data in the HR diagram, you can see the patterns that hint. Let's think this. Patterns that hint how stars are born, how they age, and how they die. If you label an HR diagram with the masses of the plotted stars, as in figure 820 we did in the beginning of this lecture, you will discover that main sequence stars are ordered by mass. The most massive main sequence stars are the hot and luminous stars. As you run your eye along the main sequence down to the right in the diagram, you will find successively lower mass stars until you reach the lowest mass, coolest, lowest luminosity main sequence stars. So here we can see upper main sequence O stars are the most massive stars. The lower main sequence red dwarfs are the lowest mass stars, then the giants and supergiants. Stars that do not lie in the main sequence are not in order on the HR diagram according to mass. Giant and supergiant stars are a jumble of different masses. Although supergiants tend to be more massive than giants, in contrast, all white dwarfs have about the same mass, somewhere in a narrow range from 0.5 to about 1 solar mass, because of the systematic ordering of the mass along the main sequence. The main sequence stars follow a mass-luminosity relation. The more massive a star is, the more luminous it is. Although giant and supergiants follow different mass-luminosity relations, and white dwarfs do not follow one at all, the link between mass and luminosity is critical in astronomy. The density of stars reveal another pattern in an HR diagram. The average density of a star is its mass divided by its volume. As you will learn in the next chapter, stars are not uniform in density, but are most dense at the centers and least dense near their surfaces. The center of the Sun, for instance, is about 150 times as dense as water, 50 times as dense as lead. Its density near the visible surface is about 3,400 times less dense than Earth's atmosphere at sea level. The Sun's average density is approximately 1 gram per cubic centimeter, about the density of water, intermediate between its central and surface densities. Main sequence stars have average densities similar to the Sun, but giant stars have low average densities ranging from 0.1 to 0.01 gram per cubic centimeter. The enormous supergiants have still lower densities, ranging from 0.001 to this number grams per cubic centimeter. The white dwarfs have masses about equal to the Sun's, but are very small, only about the size of Earth. That means the matter is compressed to enormous densities. On Earth, a teaspoon of this material would weigh more than 5 tons. Density divides stars into 3 groups. Most stars are main sequence stars, with densities like the Sun's. Giants and supergiants are very low density stars, and white dwarfs are high density stars. So here we can see the relationship. The mass-luminosity relation shows that the more massive a main sequence star is, the more luminous it is. The open circles represents white dwarfs which do not obey this relation. The red line represents the equation, so this is just basically the formula for the line. And that gives us luminosity equals mass to the power 3.5. So now we can do reasoning with numbers again. The mass-luminosity relation. You can estimate the luminosity of a main sequence star based on the star's mass. Main sequence star's luminosity in terms of the Sun's luminosity equals its mass and solar masses raised to the power 3.5. So this is a mathematical form of the mass-luminosity relation. It is only an approximation as shown by the red line. So in figure 8.21, but it applies to most main sequence over a wide range of stellar masses. So an example, keep this in mind for tests and exams. What is the luminosity of a main sequence star with 4 times the mass of our Sun? So, solution, we take our formula, we plug in 4, and we get 128. So it's 128 times more luminous than our own Sun. So now I want to show you another animation. Yes, neutron stars we are also going to discuss. And if you see this illustration, that brings us to the classification and the senses of what stars is. Do you guys have any questions? Any questions? Why is everybody so quiet tonight? Did you guys have a hectic week, tests, exams, assignments? What are you guys writing on Wednesday? Okay, so spectroscopic binary stars. So let me explain the spectroscopic binaries again. Okay, so in spectroscopic binaries, so the three types of binary systems we have. The first one we talked about, let me just get to it, is visual binary stars. So that means when you look through a telescope, you will see a big star and a big star and a small star orbiting a central point of mass, and you can clearly see both with your naked eye or through a telescope. But sometimes these stars are so close to one another that through a telescope, you can't distinguish them. So one way you can distinguish this binary system is by looking at its spectrum. So what would happen is, in a normal star system with one star, we will see the spectrum of the star, and we will see our normal origin Balmer lines, the absorption lines of origin. But when it's a spectroscopic binary, meaning there's another star, and we look at the spectrum of the star, we'll see double lines all of a sudden, close to one another. And that means that there's actually, we are looking at two different stars at the same time, and not one star, if that answers your question. May, I have no idea. I have to look at moonrise and set times. If you send me an email, then I will be able to assist you. So I'm going to leave it open to you guys. We can call it the evening. I see our time is almost up, or we can end with end of the lecture with one more video. So about a graph, when we discussed eclipsing binary systems, what do the dips represent? That's dips in luminosity. So that's when one star blocks the light of the other star, so you have less light reaching us. So it's safe to say that a binary system consists of two stars where one is big and the other is small, or is this case where, okay, so usually in a binary system, you have a larger star and a smaller star. Sometimes in very rare circumstances, you'll get stars that's almost the same size, but one has to be larger than the other one to get a binary star, because you need a stable system. So if you have two that's exactly the same size, that will mean the gravitational effect on both will be the same, and they can cancel each other out. So you need to have one star that has a larger mass than the other star. Yes, so let me get to that graph again of eclipsing binaries. So yes, here we will have the big dip when the small star is blocked out. So we will receive basically no light from this star, only from this star. But the small dip will be when the small star is in front of the big star, meaning we will block out a little bit of the big star, but we will still be able to see the majority of bursts of the light from both. So to end off tonight's lecture, I'm going to show you guys a video of, so I will watch it later. So the videos are, so everything is recorded this evening. It will be uploaded to Google Drive and YouTube. So if you want to watch it later, if you log in through the UP Connect portal and go to the Google Drive link and you download it, it will be 0 data rated. Otherwise, you can watch it on YouTube as well. So let me just get this started. So these are two short videos I'm going to show of, you probably heard me spoke about the Green Bank Observatory before. So I've spent some time at a Green Bank Observatory as a visiting scientist.
GBT is the largest fully steerable radio telescope on the planet. It's one of the largest moving structures on land. It stands 485 feet above ground level, which makes it taller than the Statue of Liberty, weighs almost 17 million pounds. So with 16 wheels, more than 1 million pounds per wheel is transferred to the foundation. Like a bigger bucket collects more raindrops, the GBT's large surface area can collect more radio waves from space. The reflecting area is 2.3 acres. So a football stadium would fit inside of that.
So radio telescopes are just one window onto the universe. So when you think about astronomy, often people think about your classic optical telescope, something you can stick your eye up to and you can look through and you get to look at a picture of a galaxy. A radio telescope is the exact same idea, only instead of looking at the optical waves, the stuff that you can see with your eye, it's looking at radio waves.
We're trying to take the principles, the things we understand about chemistry from the laboratory, and apply those to molecules in space. Understand how you can build up things that lead to the formation of maybe life from what we see starting out in the earliest remnants of dead stars and the birthplace of solar systems.
The light coming from the galaxy we're looking at is about as old as the Earth is now. The GBT is especially good for this. It's so massive, its beam is very small, it's incredibly sensitive for this kind of work.
The sensitivity of the GBT is 10 to the minus 29 watts per square meter per hertz. Now, to put that in a term that you can understand, it can detect an energy level that's equivalent to the energy given off by a single snowflake hitting the ground. A typical quasar in space gives out a billionth of a billionth of a millionth of a watt. So it takes very sophisticated and very sensitive receivers to detect those signals and be able to process them in a manner that the astronomer is needing.
How many kids haven't looked up at the sky and just said, what's up there? And astronomy is able to talk to them about that and keep that curiosity going. So that kid who is curious about astronomy may turn out to be the next best physicist. They may turn out to get a Nobel Prize solving something in medicine. But it all started because there was somebody willing to answer their questions about what's up in the sky.
Okay, and the last video for this evening I'm going to share now. Yes, for real as a snowflake. That's why it's such an amazing instrument.
Everyone that lives here has to sign a form stating that they will not own a microwave or a wireless telephone or Wi-Fi. Just about anything that uses electricity could potentially cause interference to our telescopes.
Mostly cloudy skies are in the forecast for tonight. Heavy showers are likely and isolated thunderstorms through evening. Close tonight in the upper 30s.
Green Bank and Pocahontas County in general, I think, is a very interesting place. It's very much anchored by a few institutions like the state parks and the wilderness area, the ski resort, the observatory. I'm Felix J. Lockman, and I'm the Green Bank Telescope Principal Scientist. I'm an astronomer on the staff here at the National Radio Astronomy Observatory in Green Bank, West Virginia. The Green Bank Observatory was established by the National Science Foundation as a place that could offer world-class facilities, and it's used by astronomers from all over the country and even some other parts of the world to study objects like stars being formed or new planets or galaxies like the Milky Way, even the remnants of the Big Bang. It's a very amazing combination of the highest tech and yet kind of 1950.
I was born and raised here in Pocahontas County and saw the telescope being built piece by piece every day as I drove by to school, essentially. I'm actually a radio frequency technician. I work with the sensitive receivers that are on our telescopes. I essentially patrol the area, if you will, for radio frequency interference so that astronomers can do their job and study the cosmos.
When I first traveled here, I lost service coming up Sheep Mountain, and I was just like, okay, maybe it'll come back when we get to our destination. It never came back. I didn't know what to do. I was so hooked on my cell phone. It was just kind of a shock to me, like, really? They actually have something like that where you can move to and there's no cell phones, no anything. I grew to like it. I did.
In the absence of cellular technology, you plan ahead a little bit. You tell your friend where you're going to meet them. It's just, it's hard to imagine it being a requirement of life.
We enjoy coming here where we don't have people say, well, give me your cell phone number. What's your internet access? Do you have Facebook? Do you have Twitter? No, we don't.
Unfortunately, in many places we live, we don't know the neighbor that's maybe immediately next door, and sometimes definitely not the one that's 2 or 3 houses, but most people here have some idea who their neighbors are, and many times by name or by personal contact.
People in larger cities sometimes forget that you've got to make a human connection. It's not just a matter of getting the best job and making the most money. I've never felt such a strong sense of community until we moved here.
It's a great commitment by the United States to have some little sliver of money for pure basic research. That amount has been decreasing in the last 10 years, and so we're really feeling the strain of that here now.
Any nation that has been on the cutting edge of history have been nations that have been interested in exploring and looking at the cutting edge of technology and science.
And I think a lot of astronomers are trying to figure out, why are we here? You know, we can look into outer space, look back through the ages of time and learn about so many different things. I don't fully understand the distant galaxies and all of the objects that scientists want to study, but I know it's important. I'm sure there will be a lot more to come.
So I see it's a bit cloudy there. How much does this affect the telescope, or does that affect, because it's straight away? It doesn't affect the telescope at all, because we're looking at the rest of the electromagnetic spectrum and not at visible light. So ladies and gentlemen, this was tonight's lecture. If you have a few more questions, I'll remain active for a minute or two. Otherwise, you guys are more than welcome to log off, and I will see you all tomorrow night.